So in this section, we will discuss how to make Lebesgue functions smooth, more precisely infinitely differentiable via convolutions and mollifiers. So let's start with the definition of a convolution. So given two functions, say f and g, from Rn to Rm, the convolution of f and g at a point x in Rn is defined by, so the convolution will be denoted by an asterisk or a star, and this is the integral over Rn of f of x times g of x minus y dy. So this should be instead f of y. Provided that this exists. Okay, so for instance, functions having compact support, f and g makes this integral well defined. This convolution is commutative and also associative. Again, of course, whenever these convolutions exist. So that's commutativity and associativity. So the order of convolution and the grouping is immaterial. Again, let us emphasize that as long as these convolutions exist. Another case, if f and g are in L2, then the convolution is also well defined, and you can simply apply, let's say, the Cauchy-Schwarz inequality and the translation invariance of the Lebesgue integral over Rn. Okay, now, and of course, you need to apply the transformation rule. And that remark, in fact, can be generalized. And there is what we call the Young's inequality. For convolutions. So let's say I have PQR, wherein the sum of the reciprocals of P and Q is the reciprocal of R plus 1. You can think of this extra 1 here as the integral in the application of a Holder's inequality. If F, let's say, is in LP, Rn, and G is in LQRn, then the convolution is in LR Rn. And the norm of the convolution is less than or equal to the product of the norms. So I will not give the detailed proof, but let me give you the hint. So here you need to apply Holder's inequality and the Fubini theorem. So I will leave that for you to check. So in this lecture, we will use the following abbreviation. So we will, let's say, denote the LP norm by, or the LP norm in Rn, simply by LP. This point, our domain would be the whole Euclidean space Rn. So we will ignore at this point, the notation Rn to simplify things. Okay, our main result for this section would be the density of, so let us put the goal, the density of test functions in Rn in LP. This is dense in LP Rn, of course, for P that is finite, greater or equal to 1. So this is our goal in mind. So in the previous discussions, we only know so far that the space of continuous functions having compact support in Rn is dense in LP. But in fact, we can go further into a smaller subset, and we can take the infinitely differentiable functions with compact support in Rn, and that a subset is also dense in LP. And in order to establish this, we need several lemmas. So for the first one, we would like to establish the existence of a test function, okay, with the following properties. So the values are between 0 to 1. The support phi is in the closed unit ball. Phi is positive on the interior or in the interior, and it is normalized. In other words, the integral is equal to 1. So here we have a test function with these properties. And as such, a test function will be called a mollifier. So existence of a mollifier. So for the proof, let me give you the main ideas, and you can work out on the details. So first, let us consider two positive parameters, R and capital R. R is smaller than capital R. And define the real valued function, say G, as follows. So g of t is e raised to negative 1 over t. If t is positive, if t is less than or equal to 0, then we just define it to be 0. Okay, so just to visualize this function, so it is 0 when t is less than or equal to 0, and it is positive, and it is asymptotically 1 as t goes to infinity, because the exponent will tend to 0, hence the exponential will tend to 1 as t goes to infinity. And as t goes to 0, the reciprocal 1 over t goes to infinity. Therefore, the exponential tends to 0. Hence, you have continuity. And in fact, by induction, you can prove that the kth derivative of g would be pk of t, 1 over t, for t greater than 0. And this is equal to 0 for t less than 0, where or for some piece of k that is polynomial. This is done by a repeated application of the chain rule and the product rule, and also by induction. Then you can notice that the limit as t goes to 0 of this exists, and in fact, it is equal to 0. So this implies that, in fact, g is infinitely differentiable. Okay. So although this is piecewisely defined, it is in fact smooth. By smooth, we mean infinitely differentiable. Okay, so we want to have a function that is, let's say, supported in this closed interval. So the main idea is to consider a translation. So let's say this is gt minus r. We do that also, and then after reflection, this will be your gt capital R minus t. And then we take the product of these two functions. So we define the product to be f. This is the product of these two functions, one that is being translated, the other one being translated and then reflected. And you can see that the support of f is this closed interval. Okay, I want to, let's say, to have a support that is on the left side. Okay, so what we do is, let's say, or support in negative infinity to r. So what we would like is that if we go beyond this line or this point, the value of your function is 0. And one way to do that is, of course, by considering the following integral. This should be f. Okay. So as you go, since the support is only on this interval, if you integrate starting at a point larger than r, since the function is 0 beyond r, then this integral would be 0. Okay. And finally, so this our function from r to r. Finally, let us define this function from Rn to R as follows. So phi r of r of x is your function divided by, okay, let us normalize. Let us take the integral from r to capital R. Okay. Well, here you can say from negative infinity to r, the support of h. But that would suffice. But it is sufficient to consider from R to capital R since F has support in this interval. Okay, so this is H of STS, and this one is the Euclidean norm. Okay, then please verify that this function satisfies these properties. So the values are between 0 to 1. The support lies in this closed ball. Okay, because if your radius is beyond R, your function would be 0. And this is identically 1 on the smaller ball, B0R. Okay, and that follows immediately from the definition of H. Okay, these are not yet the one that we would like. So going back to, okay. So if we take, let's say, capital R to be 1 and small r to be 1/2, then we have this property. Okay. Then we can take phi to be phi 1/2 1, as there's no reason that the integral of this function is 1. So we normalize. So we just basically divide it by the integral, so that the integral of phi would be equal to 1. Okay. So a function, a test function on this lemma will be called a mollifier. So let's start with that. Based on this modifier, we define a new function, phi sub k. This is k to the n, phi kx. So this is a function from Rn to Rn. Okay, this function satisfies these properties. So phi k, since this is a multiple of a modifier or test function, and you have some sort of a scaling of the argument, since those are what smooth operations, then this scaled a function phi sub k is also a test function. But now the support lies in the smaller ball. So the support will be dilated due to here we have an expansion of the argument. This is positive on or in the interior, and the integral is also equal to 1. And this is the reason why we have this factor here. You apply, let's say, the transformation rule for Lebesgue integrals. Since you are dealing with multi or an n-dimensional domain, then you should multiply the factor k times. So these properties are, or these properties follows immediately from the properties of the mollifier phi and the definition of phi sub k. Okay, so consider a locally integrable function u in Rn. If let's say we consider the convolution to the point x, by definition, this is the following integral. But then take note that phi vanishes outside its support, so it is enough to integrate this inside the support of your function. So if x here is not an element of the support of u plus this set, okay, what is the sum of two sets? In this case, we define it to be the set consisting of all sum of elements in the support of u and this closure of the ball centered at 0 with radius 1 over k. And what is the support of a locally integrable function? Of course, we need to define this because pointwise evaluation, take note, is not well defined on Lebesgue functions, because modifying a function at a single point gives you the same function almost everywhere. So here the support is basically Rn minus the union of all open sets omega, small omega, where u is 0 almost everywhere in omega. So you remove the sets wherein of course omega is open, okay, where your function u is 0 almost everywhere. take note that this is open. So the union of open sets is open. And I should replace this by Rn since that's our domain. Okay. And take note that this is a closed set because this is, let's say, a complement of an open set. Okay. So that's the support of an locally integrable function. Then if x is not in this set, this will vanish. Okay. And with that, we can see that the support of the convolution is a subset of, okay, we should put the conclusion here. So if x is not in that set, this is 0. Hence, the support of your convolution lies in this set. Okay. So a convolution will give you a larger support, but if k is large enough, okay, the distance between the two supports will be small. So as an illustration, here imagine the black region to be the support of your locally integrable function. So what you do is you add this by this set. So that is the larger set colored in blue. So that's the support of u plus the closure of the ball B01 over K. And in this case, the support of the convolution would be a subset of the blue set. So that's how, in this case, the support of the convolution behaves. So it will be, it will be contained in this sum of two closed sets, the support of U and this closed ball. So that's the behavior of the supports with respect to the convolution of our scaled multipliers. The next lemma would be the following. So suppose I have a continuous function having a compact support p between 1 to infinity. Then this convolution tends to V in LP. Okay, so if you let the parameter k tend to infinity, then you end up with the original function V. So for the proof, let us first consider the case where p is equal to infinity. And let us denote S sub k to be the support of V plus this set, this closed ball. So this is the same set, but with U replaced by V in the above discussion. We are going to estimate the difference of the convolution and the function V in L infinity, or L infinity Rn. So this is less or equal to Okay, so it is enough to take the supremum over all x in S sub k, since the support of the convolution and V lies in S sub k, and then enough to integrate over this ball for the different. This is phi ky. Here I am applying the definition of the convolution, and I also used the fact that the integral of this test function is equal to 1. Okay, so that's good so far, and this goes to 0 by uniform continuity of V on, let's say, the largest set, that is S1. Take note that this is decreasing with respect to K. And in fact, this one will converge to 0 uniformly, and therefore the integral, hence the supremum in this case. And you can easily establish this by using the definition of uniform continuity. So please check the details. Now, if P is finite, then you can simply apply the previous case and Holder's inequality. So this is, of course, as we said, enough to consider the LP norm in S sub 1, the largest support of the convolution, and by Holder's inequality, this is less than the Lebesgue measure of S1 raised to 1 over P times the L infinity norm of the difference. And we already know that this goes to 0 as K goes to infinity. So again, in this lemma, convolution of C sub 0 function in Rn converges to the original, or to the given function V as K goes to infinity for the sequence of mollifiers that we have discussed last time. Another lemma before we prove the density that we have alluded a while ago. So although the previous lemma is valid when P is equal to infinity, the following lemma will be only in the finite case. So if I have a U in LP, then 1, the convolution smoothens the function U. So in other words, the convolution is continuously differentiable, and it is a contractive mapping. So convolution gives you a norm that is lesser than the, or possibly equal to the original function. So this is smoothing and non-expansive. I will not give the proof, but you can, let's say, apply the Lebesgue-dominated convergence theorem for 1, or to get 1, and Young's inequality with obviously R equal to P and Q equal to 1. This one refers to the integral of the mollifier. And of course, the integral of this mollifier phi sub k is equal to 1. So that's why you do not see an L1 norm of phi sub k here. To obtain the second part. Okay, so we are now in good position to prove the density. In fact, it will be a consequence of the first statement of the following theorem. So again, P is greater or equal to 1, but finite if U is in LP Rn, then the convolution tends to U as k goes to infinity in LP Rn. Okay. So that's, let's say, the first one. Now the second one. This is dense in LP. And we will prove this using the first convergence. Okay, so what we know so far is that this is true. The first one is true in the case of a function having a compact support. But first, take note that this is the place where we need this. So since this is dense in LP, this was shown in the previous lecture. So given a positive epsilon, there exists a V in C sub 0 Rn such that the distance between U and V in LP Rn is less than epsilon over 3. Now, also, we know from the previous lemma, this convolution tends to V in LP as k goes to infinity. And where is this? This is the lemma going back above this one here. Okay, since V is now a continuous function with compact support. So if this is true, then one can find, let's say, a sufficiently large positive integer such that, according to the definition of the limit, the difference, this difference is also less than epsilon over 3 for all k greater or equal to n. Okay, so now we add and subtract terms and then apply the triangle inequality. So first, let us say, so our goal is this convergence. So let us take the difference. U. Now what I know is this one. So it is natural to subtract V. And then if you apply triangle inequality, okay. But then you have what? You know this information here. So you subtract this convolution. And then you now adjust. So you again add this convolution of with respect to V. And then consider this last term. Okay, according to the definition of the convolution, this is, okay, let us include the norm. This is equal to the norm of this one. So we just apply the definition of the convolution. And this is less than V minus U, LP. This is from this lemma and this second part. So convolution does not, or a convolution is, as I said, a non-expansive map. Okay. So this term here is the same as this one. And we know that the distance between U and V is less than epsilon over 3. So we have that. And we also know that this is less than epsilon over 3 for, of course, k greater than or equal to n. Hence, we have the following. U minus the convolution phi sub k star U, LP norm, is less than epsilon for any k greater than or equal to n. And this is precisely 1 of the theorem, this convergence here. Okay, how about density? For part 2, everything has been set up. So note that phi j, this is infinitely differentiable, and it has compact support. And the fact that, okay, should be k. The fact that this is C infinity follows from the second part. How about the compactness of the support? Again, recall that the support of the convolution, this convolution is a subset of the support of V plus this one. And you can show immediately that this is compact. So the sum of two compact sets is again compact. So what you do is, if you have a covering of the sum, then that would be a covering on each set, let's say up to probably translation, okay? And you apply the compactness to reduce the covering to a finite subcover on each of the two sets. That is the support of V and this closed ball having radius 1/k. And with this, we now have for k greater than or equal to n, let us take the difference of this in LP, and let us just emphasize, okay, that this is C0 infinity Rn. This is less than or equal to, okay, using the same technique. We subtract V and then add V. Applying the triangle inequality, we will have this. And the sum is, according to the construction above, is less than 2 epsilon over 3, is less than epsilon. Okay, so given an arbitrary U in LP, we can find an element in this space that is close enough. In other words, less than this arbitrary given epsilon. And this ends the proof. Of course, one can obtain the same result even when you only have an open set in Rn. Okay, so this is dense in LP omega. And as usual, for P, a finite set. Okay. I will not give the proof. You can check the proof in the course notes, but the main idea is to extend this C0 infinity function or C0 omega function into the whole of Rn, and you apply the previous result. So you just apply the density of this function in LP and extend by 0 outside omega. So you can make an LP function close to a C sub 0 function. So a C sub 0 function would be 0 on the boundary. So you can extend outside the boundary to get a C0 function in the entire domain, in the whole of Rn. Okay. Well, the integrability follows immediately since V, let's say the function V in C naught omega will have a compact support. And as an application, we will consider later the fundamental lemma of calculus of variations. And this will be done in the next lecture.